Good morning. Welcome back to the first section of Chapter 12. This is the last chapter that we will be looking at this year. So you can calm your crying. It'll be okay. Anyway, this chapter is on sequences and series. Today we're just going to look at what is a sequence, and we're going to see some notation. And so our learning targets for today, I can find the nth term of a sequence, and I can write rules for sequences. That'll be like writing a formula. So, first question, what is a sequence? A sequence is just a list of numbers separated by commas. That's all it is. Something like 5, 7, -2, 5.43, pi. That's a sequence. Most of the time our sequences will have a pattern that goes along with it because we're not going to write an equation to match this. It's just not going to happen. And we have two basic types of sequences that we'll be looking at. We have finite sequences and infinite sequences. Finite sequences just have an end point. It has a finite number. Like this one up here was a finite sequence because it stops. 2, 4, 6, 8, 10 is a finite sequence. Most of the times we'll have infinite sequences. With an infinite sequence, we just have to develop the pattern, and then we can go ... 3, 8, 13, 18, ... What would the next one be? 23, then 28, 33, 38. And so we can just keep going like that. And so that's what a sequence is. And again, most of the time we'll be working with infinite sequences just because they keep going. And you can always cut it off at a certain point. Next thing is our notation. Sequence notation uses a sub n. A would be the name of the sequence. We usually start with A and it's lowercase, and n would be the term number. This is basically identical to f of x, where f is the name of the function, and then x is the value we plug in. The difference, x is generally a real number, whereas n is a whole number. 1, 2, 3, 4, 5. We don't have the n plus 1th term. And each of the numbers in here is a term, not n plus 1th. We don't have like the 1.5th term. And so each of these are terms. This is first term, second term, third term. And we can notate that with a1 is the first term, so in this one it would be 2. And then a2 would equal 4. Then a3 would equal 6, etc., etc. And then an would be the function itself, or the sequence. And so we have two different types of formulas that we use, and these could be used for both infinite or finite sequences. The first type is a recursive formula, and the second is an explicit formula. A recursive formula uses previous terms to define the term that you're talking about. So if we have, say, 3, 6, 12, 24, 48, we can see what are we doing each time. Hey, we're multiplying by 2, then times 2, then times 2. So we can just take the previous term times 2. We have to start out with the first term because we have to have a starting point. a1 equals 3, and then an is just 2 times the term before it. So a to the a4 is 2 times a3. a17 will be 2 times a16. Now the problem with this is in order to find a17, we need to know what a16 is. To do that, we need to know what a15 is, etc. So we have to get the entire sequence up to that point. But sometimes we can only write it using a recursive formula. For example, the Fibonacci sequence, very famous sequence, looks like 1, 1, 2, 3, 5, 8, 13, 21, etc. I have it on probably 3 or 4 posters in my room. And what we do, it starts out with 1, 1, and then each number is the sum of the two previous. 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8, 5 plus 8 is 13, etc. And so, for this one, since we use two numbers, we have to define both a1 equals 1 and a2 equals 1. And now an is the number before it plus the number before that. So these would be the two previous numbers. So if we wanted to find a7, that'll be a6 plus a5. But again, in order to find that, we have to get all the way up to there. Now, an explicit formula is like what we've been doing with functions for the past year. Our functions have been explicit functions, and that just uses the term number. Our functions just use x. This will just use n. So if we start out with, say, the same one, 3, 6, 12, 24, 48, well, we're multiplying by 2 each time. That sounds like an exponential equation. And so we'll have 2 to the power, 2 to the n. Well, 2 to the 1 is 2 times what equals 3? 3 halves. 2 squared is 4 times 3 halves. And so we have 2 to the n times 3 halves. This one's a little bit tougher to find out, but we can figure out what the 17th term is without finding any of the others by just plugging in 17. A little bit easier one, let's look at back at this 3, 8, 13, 18 that we saw on the last slide. What are we doing each time? We're adding 5. Hey, if we're always adding the same number, isn't that linear? Yeah, so we'll have 5n. Let's see, 5 times 1 is 5. How do we get to 3? Minus 2. 5 times 2 is 10. Minus 2. 5 times 3 is 15. Minus 2. So an is just 5n minus 2. And we'll look at how we can do these a bit more specifically for different types throughout this chapter. Right now it's just an introduction. You're just kind of looking at it logically and intuitively. Anyway, that's section 1. I will see you on Monday.